Okay. Prop 33 says the straight lines joining equal and parallel straight lines at the extremities, which are in the same directions respectively, are themselves also equal and parallel. So, on the one hand, whenever there are sort of these little lines that are in the square brackets, that's something that Heath added in. It's not in the original manuscripts or sources that are existing. It's something that Heath added in for clarity and for mathematical rigor, and here it's just to make it kind of like more clear what we're talking about. So the setup here is, imagine that we have two lines, AB and CD, that are both parallel and they're also equal in length. Then if you join the extremities of each of those sides, kind of like respectively, so joining A to C and B to D, the claim is that AC and BD are equal in length and they're also parallel to each other as well. So that's what we want to prove. Okay. And I guess I'll write that out because to me I think the proposition is, like a lot of them, it's kind of strangely worded. So in my proof I'll actually say, rewrite again what we're given, and maybe not what we're going to prove, but at least what we're given. So assume that AB equals CD, and more, AB is parallel to CD. And then we join, just assume that we've joined AC and BD. I'm not going to mention that in here just because it's not actually part of the proof, but, we're talking about those lines, so those lines do have to exist. All right. So the first step is we're going to join BC. All right. And once we join BC, it probably becomes a little bit more obvious exactly how we're going to go about proving this, because joining BC is going to create two triangles. And if we have two triangles, we can start talking about them. If we can prove that they're congruent, we're in a pretty powerful position. Okay. Well, what do we know? We know that AB is parallel to CD and BC is falling on them as a transversal, essentially. So, then we know, what do we know? We know something about the angles. We can say that angle ABC, so this top angle up here, is going to be equal to this angle down here, BCD. And that was from Prop 29, which says if you have parallels and then you have the transversal, it says something about the angles. Okay, then let's take a look again at what we have. So we just said that ABC is equal to BCD. We're given that AB is equal to CD, and then this side BC is in common. So we have a side angle side congruence. So, since, and I'll just kind of restate it, since AB equals CD, angle ABC equals angle BCD, and I'll write BC equals BC, although the way that Euclid says it is they have BC in common. It follows that, and he states out, he states the whole conclusion of Prop 4, which can be summarized as the triangles are equivalent. But the main point of what we want is a couple of angles. So I'll say, since this is true, triangle ABC, you want to be kind of careful with the ordering. ABC is the same as, looks like, DCB. The ordering kind of indicates like what sides correspond to what sides, what angles correspond to what angles. Right, so ABC, BCD, yeah, they're the same thing, same angle. And this is by Prop 4. Side angle side. So, specifically, I guess, maybe I'll say in particular, we have, just to fill up some space there, angle ACB is equal to angle CBD. So ACB is sort of this angle right here is equal to CBD, this angle up here. Right. Okie dokie. Well, why is that useful for us? Can you see? It's kind of it's an argument that almost feels a little bit circular, but it's not. It's not circular. It's perfectly sound. What we point out now is, oh, okay, well then we have BD and AC are two lines that have this transversal BC, where ACB is equal to CBD. And we have a proposition that says when you have two lines, another line falling on those two lines that makes those particular angles equal to each other, then these lines are parallel. I just realized too that I actually, based off of this last one in particular, we have this angle, and I should also note, and since these triangles are the same, we also get that AC is equal to BD. Sorry, I kind of skipped over that, but this just follows from this same step. So since triangle ABC equals triangle DCB, AC equals BD, and this is still true too. So AC equals BD, but I needed to state that. I needed to state that because that was part of the conclusion, is that not only are these lines parallel, they're also equal. So here's where I've just proved that they're equal. Let's see. Oh, gosh. I feel like it's stated wordly. I feel like I should put these in parentheses or something. But because this next line follows because of the angles, I just stated this kind of funny because I forgot about saying that. But in particular, we have these angles are the same, so maybe I'll just do this just to make it really obvious that this is actually what leads to this next line. So maybe I'll say since AC and BD have the transversal BC, and angle ACB equals angle CBD, it follows that AC parallel to BD. And that was from Prop 27, was it? Or 28? Yeah, 27. I can kind of never keep them straight. Right, and that's what we needed. So the lines are equal, and they are parallel. Yep, there we go. QED. Oops. A little off screen, sorry. Therefore, etc.